This is the first in a series of videos about colligative properties. We'll be talking about the definition of colligative, molality, vapor pressure lowering, and boiling point elevation and freezing point depression. So we'll start with the definition of what colligative properties are. So colligative properties, it's a name for a group of properties that all have one condition in common. So these are properties of solutions, because this is the solutions chapter, that only depend on the amount of solute, the smaller piece, and not on the solute identity. Okay, so here's the thing that matters. It only depends on the solute amount, and we like to call that the how much. So in every formula that we learn about that's a colligative property, there's always going to be some sort of a term indicating how much, and it doesn't depend on what it is. So let's talk a little bit more about this how much factor. So we're going to have to introduce some new math this chapter. There's a couple of different ways that we express how much in these formulas. One of them is called the Van 't Hoff factor. One of them is the mole fraction, which we talked about in the gas law chapter. And one of them is a new unit of concentration called molality. And some examples of the colligative properties we're going to be talking about in this chapter. We will talk about vapor pressure lowering, boiling point elevation, and freezing point depression. Okay, so let's start out by talking about all of our different measures of how much, so we're ready when the formulas hit us. So we're going to start out by talking about electrolytes and the Van 't Hoff factor. So this is a measure of how much. Okay, so an electrolyte is a word you might have read on a Gatorade bottle in the past. So an electrolyte solution is one that produces ions when dissolved. It specifically describes the solute. When the solute is dissolved, it produces ions. So here's an example. If I dissolve 1 mole of sodium chloride, once it fully dissolves in the solution, we know that these sodium chloride units are not going to stay together. They're going to split into 2 separate ions. And so we'll have 1 mole of sodium cations, and we'll write aqueous because it's dissolved in water, and 1 mole of chloride anions. So while we dissolved 1 mole of this substance, the number of ions in the solution is actually 2 moles because these units, these formula units, split in half. And we can't assume that this ionization always moves at 100% efficiency. So we can describe this qualitatively with our little bar graph here. Okay, so if the ionization process is not particularly efficient, it's somewhere here at the low end. We call it a weak electrolyte, meaning that not all of it dissolves. We'll say that it's from low to like maybe this high. Probably shouldn't even draw it this low. If it's that close to 0, it doesn't even dissolve at all. And if it's up here near the 100, then we call it a strong electrolyte. Up here close to 100%. So let's change weak electrolyte. Let's make it here. And then let's make this region something else. So this is weak electrolyte here. Strong electrolyte is this one. And then down here at the bottom, if it's this close to 0%, it really doesn't dissolve into any ions, then we'll call it a non-electrolyte. A non-electrolyte produces no ions when dissolved. So this is some sort of generic non-ionic compound. We can give an example here. Glucose, C6H12O6. If you were to dissolve that in water, all of the glucose molecules would stay together. They wouldn't split into their pieces. It's not an ionic compound. So we would just write 1 mole of glucose aqueous. So the number of moles that we put into the solution of the initial formula unit is the same as the number of pieces in the solution. Okay, and so now that we've seen that there's a difference, some things dissolve to give more pieces and some pieces dissolve to give fewer pieces, we have a factor that we can use to describe that ionization process, and that is called the Van 't Hoff factor, and it's represented by the letter I. Probably for ion, I would guess. And so I is a ratio of the number of moles of dissolved pieces, usually ions, divided by the moles of formula unit. And this might be an unfamiliar term for you. The formula unit is just the unit that you put into the solution. So the sodium chloride or the C6H12O6, that is the formula unit that I put into the solution. So let's give an example of these. Okay, so in my non-electrolyte example, I said that glucose it started as one piece and it ended up as one piece. There was no separation that happened. So our Van 't Hoff factor for that is 1 piece at the end over 1 piece at the beginning. In our electrolyte example, we used sodium chloride and we said 1 initial piece went to 2 ion pieces. So that's going to be 2. And we can even go higher than 2 if we were to find something with more counter ions in it. Here we go, sodium sulfate. So each one of these sodiums is going to be a piece, and then this SO4 2- is going to be its own piece. So there are going to be 3 pieces in solution over 1 formula unit. I is going to be 3. And so it's as simple as that to figure out the Van 't Hoff factor for your compound. Okay, and then we'll throw in, that's this one. We'll throw in our second one, the mole fraction at the bottom, even though we already know what that is from the gas law section. Mole fraction is our second way of measuring how much. Okay, and we remember that our mole fraction is going to be the moles of A over the moles of total. There we go. Quality was a little bad there for a second. Moles of A over moles of total is our second way of measuring how much. And in the next video, we'll look at the third way of measuring how much, which is the molality.